Hello everybody and welcome back to Chem Talk, where today we'll be talking about the standard enthalpy of formation. Now, what is the standard enthalpy of formation? So it is a measure of energy released or consumed when 1 mole of a substance is created under standard conditions from pure compounds or pure elements. And what the definition of pure compounds and pure elements we'll get into in a little bit. Now, the sign that represents standard enthalpy of formation is delta H standard F. And you're going to see that standard is this little circle degree above. And when we're going through what this whole kind of phrase means, our delta means our change in enthalpy. Our little degree sign is our standard conditions for the enthalpy change. And our F is when the substance is formed from pure elements. Now for our equation, we're going to see that our delta H standard F equals the sum, which is this weird looking 3 over here, or E, of our delta H standard F of our products minus the sum of our standard enthalpy of reactants. So we're going to see that it's again energy of products minus the energy of reactants equals our total standard enthalpy of formation. Now, under standard conditions means that our pressure equals 1 atmosphere or 1 atm. It also can be made into 760 millimeters of mercury or 760 torr. And our temperature is going to be 298 Kelvin or 25 degrees C. Usually this information comes into handy when someone's kind of asking you what the standard is. And when it's asking you for any other kinds of questions related to the energy. Now, when we're considering this following reaction, we're going to see that our carbon solid plus O2 gas equals CO2 gas. Pretty standard and pretty simple in order to find carbon dioxide. Now, the value of our enthalpy of a reaction is equal to our standard enthalpy of change for our products. So we're going to see that the total enthalpy of reactions is what is equal to the products here. When our standard enthalpy of formation value is greater than 0, we see that heat has been absorbed, and when the value is less than 0, we can see that heat has been released. Now I'm going to get into more information on kind of understanding the enthalpy of formation, just so you guys can understand what it means for it to happen and where we can get these values from. Now our standard enthalpy of formation, when any element is in its most stable form, we can see that the value is 0 kilojoules over moles. Usually the value or the units of this value is kilojoules over moles. Sometimes your professor or teacher might ask you for joules. If you're just doing that, you're going to multiply it by 1000. Now, oxygen exists as 3 different states. It exists as ozone, O3, molecular oxygen, O2, or atomic oxygen, O. The most stable form here is O2, which means that the value of enthalpy of formation is 0. And we're going to see this later on when we're doing our problem as well. Most compounds actually can't be prepared, and we can't find these values from the regular chemical equations that are defined by standard enthalpy, which is why we bring in Hess's law. Hess's law kind of allows us to see the measure of delta H in other reactions, and it allows us to get a whole table of values, which can be found in the back of your textbooks, or if you look online, we can totally find those kinds of tables on credited sites. Now, this kind of analysis is used to analyze the stability of a product. Usually it's used when we're looking at engines of cars or planes or anything that has a metallic engine. So for example, planes go to different temperatures because of different heights and different altitudes and different pressures. So you want to be able to find the most stable metal for when their planes are in kind of the middle of the air. And we want to make sure that the plane just does not fall out in the middle of the sky because the metal was not stable and then your entire engine blows. Is the same for cars, other than the fact that they are not in the middle of the air. We want to make sure that we find cars and we find metals that kind of work for the engines at different temperatures and different pressures as well. Different temperatures and different altitudes. You might be going on a mountain and you might have a different pressure there, and then the temperature is going to be different. So we want to make sure that the metal that is used is the most stable for that car and its uses. Now we're going to go into an example in order to calculate our standard enthalpy of formation. So we're going to look at the following equation, C6H12O6, and for those of you that do not recognize this is actually for glucose, reacts with 6O2 gas. Total goes to the products of 6 CO2 gas plus 6 H2O liquid. You're going to see that this equation is already balanced for us, and all we need to do is find our standard enthalpy of formation. Now I want you guys to remember that our standard enthalpy of formation change equals the enthalpy of formation of our products minus our enthalpy of formation for our reactants. Over here you're going to see that we have a little bit of a graph or a little bit of a chart to kind of find out the moles and our compounds related to our standard enthalpy of formation values. We're going to see that glucose has 1 moles, and the value related to that is negative 1,260 kilojoules over moles. All of these values are in kilojoules for moles. O2 has 6 moles, but since it is the most stable form of oxygen, we're going to see that the value is 0 over here. CO2 has 6 moles, and its value is negative 393.5. H2O has 6 moles, and its value is negative 285.8 kilojoules over moles. So the strategy that I like to follow is you figure out the value of your change in enthalpy for your products, then you find the value for reactants, and then you kind of plug it in at the end in order to just make it a lot more simpler for you. So you figure out individual terms, and then you put it into the equation to find out the final at the end. We're going to see in order to find these values, we're going to multiply our moles by that value. So for products, we're going to multiply our 6 moles, which is the moles that we have for CO2, times that value. That is going to cancel out our moles. It's going to leave us with kilojoules, which is exactly what we need. Then we're going to add that to 6 moles times 285.8, which is our value for H2O, and that's also going to cancel out our moles. For our reactants, we're going to see that we have 1 mole times negative 1,260 kilojoules over moles, and we're going to see that moles again cancels out when we're only left with the value of kilojoules that we need. For oxygen, we're going to see we have 6 moles times 0, and again, to reiterate, it is 0 because it's the most stable form of oxygen, so the value is 0, which means this entire part of our formula cancels out, which means our standard enthalpy of formation technically for reactants is just 1 mole times negative 1,260 because the other does not have a value greater than or less than 0. After figuring all of that out, we're going to see that our standard enthalpy of formation is negative 2,802.5 kilojoules over moles.